a couple of different. Okay, hopefully you have these in front of you now. So section 2.3 of this chapter takes us to how to look at other ways to take derivatives. So far we've looked at very simplistic ones in the sense that they were all polynomials, or they might have involved a trig function towards the end there. But most functions that we run across aren't that way, all right? And so this next section is going to look at how do we take the derivative of a function that's written as a product of several things, or that's written as a quotient of several things. And then we're also going to look at higher order derivatives. How do we take the second derivative of a function, or the third derivative? What do second derivatives and third derivatives and so forth mean? In the last section, just our last problem there, we talked about what the first derivative means. It means velocity. So what does the second derivative mean? So let's get started on this. So the product rule, if we have two functions multiplied together, how do we take the derivative? It would be nice if we would just say, let's take the derivative of the first and then the derivative of the second and we're done, but it's a little bit more complicated than that. So what it tells us to do is, again, this symbol means take the derivative of this, and then this is what we get when we take the derivative. All right, so at this point, it's a command to take the derivative of this, and now here we have already taken the derivative of it. All right, so it says, leave the first function alone, but take the derivative of the second one, all right, and then multiply the two of them together. All right, so it's the first function times the derivative of the second function plus the second function times the derivative of the first function, right? And that's listed right here, that it's the first function times the derivative of the second plus the second times the derivative of the first, right? But here is what it looks like when it's written out. Again, because addition is commutative, it doesn't matter if you do the second function times the derivative of the first and then the first times the derivative of the second. That's really not going to make a difference. Just really the important thing is to note that in each of the two terms, one function stays the original and the other is the derivative, and then it reverses in the second term. All right, let's look at an example. We at this point could just multiply this out and say, I don't feel like using the product rule. It's new and different and scary. And let me just multiply everything out. And I'm just going to take it using the power rule that I know from section 2.2. But there are going to be situations like this problem down here where we have no idea what to do if we don't use the product rule. So let's do this one using the product rule. We'll check it with the power rule just so we gain some confidence with knowing that we've done it correctly, knowing that it should result in the same thing either way, if we were able to multiply it out and use the power rule versus using the product rule. All right, so h of x is made up of two functions. Let's call this one f of x, and let's call this one g of x. It's nice here because it's very obvious that we have two separate functions that are being multiplied together. That won't always be so obvious because a lot of times when we multiply two things together, we don't need parentheses like this. But here this is just nice because we can see the two separate functions that we're multiplying together. All right, so it tells us that when we take the derivative of h, that we are going to leave the first function alone. So we're going to have 3x minus 2x squared times the derivative of the second function. All right, think about what that is. Hopefully you said it's 4. Plus the second function, 5 plus 4x, times the derivative of the first. Again, think about what that would be. Hopefully you said it's 3 minus 4x. All right, now let's multiply that out. You have just done the calculus part of this problem. The rest is all just algebra. So h prime of x, when we multiply this out, we should get 12x minus 8x squared plus, this is going to be the more difficult part here, we've got 15 minus 20x plus 12x minus 16x squared. Again, all just algebra at this point. H prime of x equals negative 16x squared minus 8x squared is going to give us negative 24x squared. And then in terms of the x terms, we've got two 12x's, that's 24 minus 20, so that's plus 20x. And then we've got a plus 15. Oops, but I did something wrong there. Oh, why did I say that? Sorry, I'm looking at my answer. I just said we've got 24 minus 20, so that should be 4. I don't know why I wrote 20. All right, and then plus 15. Okay, so that is our derivative. All right, let's do it off to the side here, just using our regular power rule. So before we take the derivative, let's multiply this out. If we do 3x times 5, we get 15x. Then 3x times 4x gives us 12x squared. Then negative 2x squared plus 5 gives us negative 10x squared. And negative 2x squared plus, times a positive 4x gives us negative 8x cubed. All right, so let's take the derivative of this using the power rule, which we learned in section 2.2. Before I do that, let me just clean it up a little bit. That'll save us from doing so many derivatives here. So if I just neaten this up here, I've got negative 8x cubed, goes there. Then we've got a positive 2x squared from these two, and then plus 15x. And when I take the derivative of that, I get negative 24x squared plus 4x plus 15. And that's exactly what we got over here when we did it. All right. So let's take a look at the next one. This is the part where I think things start to get a little bit harder because, again, in the last problem, we had these parentheses, which made it very obvious what the two functions were. This all kind of looks like problems that we did in the last section, right? The difference is we have our sine function, and then this cluster in front of it is not just a number, right? If you remember some of the last couple of examples we did, we had a 2 sine x, or we had a 1/2 sine x. That was not the product rule because that 1/2 or the 2 were just scalars. This, because that cluster contains a variable, this is a separate function, right? That's going to take some getting used to recognize this. But this is going to be our f of x, and this is going to be our g of x. Right? Again, because that variable is there, that now is a function, not a scalar. All right, we have no choice here but to use the product rule because we can't distribute or anything because we have a trig function here. All right, so we're going to say y prime, all right, the derivative of y is first 3x squared times the derivative of the second. All right, again, if you just look back at our last packet there that we just finished, derivative of sine is cosine, plus the second function, that's sine x, times the derivative of the first. All right, hopefully you said 6x. Now it's just a matter of using algebra to clean up. I'm just going to write this in front. All right, generally we put any algebraic terms in front of our trigonometric ones, so we would write this as 3x squared cosine x plus 6x sine x. And there's not really a whole lot that we can do with it after that. I would just leave it like that. However, if you decided that you wanted to do something with it, you could factor out the common coefficient here, which is a 3x. So you could write this as 3x times the sum x cosine x plus 2 sine x. I honestly don't care which one you use. Either one of those is fine. Okay, example 3. Find the derivative of this function right here, y equals 2x cosine x minus 2 sine x. Again, first notice we have two separate terms, right? But within this term, this cluster in front of the cosine contains an x, therefore this is its own separate function, and this we have to use the product rule for. This, on the other hand, is just a scalar, and we can just use the techniques from section 2.2. Right? So for this one, we have to use the product rule. This one we won't. For that reason, I'm just going to say this is f and this is g. And we won't worry about classifying this in any way because we're just going to use our old techniques. All right, so to find the derivative, y prime, it's the first times the derivative of the second, the derivative of cosine, negative sine, plus the second times the derivative of the first. Derivative of the first is just 2. Right? And that takes care of the derivative of this part right here. All right? First times the derivative of the second plus the second times the derivative of the first. But don't forget, I get so excited sometimes when I get through some of these larger product or quotient rules that I just forget that there's any other terms behind it. Don't forget about this. We still need to take the derivative of that. Again, this is a scalar, so we're just going to leave that part alone. And then the derivative of sine is just cosine. All right, that's the end of our our calculus. Let's go on and clean this up. This negative sign that's in front of the sine right here, let's bring that out. So this is negative 2x sine x. Again, let's bring that out front. So this is plus 2 cosine x. And then this is minus 2 cosine x. Right, these two can cancel, so we end up with y prime equals negative 2x sine x. Okay, next page. The quotient rule. The quotient rule is a little bit harder. Again, we've got two functions, f over g. They're differentiable. Two differentiable functions, f and g. That quotient is itself differentiable at all values of x for which the denominator is not equal to 0. Again, if the denominator is equal to 0, it's not differentiable there. Moreover, the derivative of that quotient is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. It looks really hard to remember. It's not too bad. Again, if you look at the top, it should remind you of the quotient rule where everybody's getting a turn here. You've got a function times the derivative of the other one, and then they switch. Here's some big differences though. First of all, product rule with sum, quotient rule is difference. Therefore, it makes a difference which order you put them in. So it has to be the bottom function comes first, times the derivative of the top, minus the top times the derivative of the bottom. If you switch those by accident, you're going to get the wrong answer. So make sure that you put the bottom function first and then the derivative of the top minus the top times the derivative of the bottom. Also, something I forget to do frequently is that the denominator has to be squared in the derivative here. All right, not the derivative of the denominator, not just the denominator. It has to be the denominator squared. Most often I just completely omit it, so don't do that. Okay, let's find the derivative using the quotient rule. So again, we're going to call the top one f. We're going to call the bottom one g, just so we can look at this. All right, again, you're going to repeat this so many times in your head that eventually you won't even have to look at it, but for right now, you're definitely going to want to look at it. All right, so it tells us take the bottom function g. All right, so y prime equals the bottom function times the derivative of the top. The derivative of the top is just 5. Again, constants have a derivative of 0, so we don't put anything there. Minus, all right, don't forget that, the top times the derivative of the bottom, 2x, all over the bottom squared. All right, that's the end of the calculus. You've done all the calculus work now. The rest of it is just algebra. So y prime equals, we're going to just clean up 5x squared plus 5 minus, let me just leave this in parentheses and distribute the back end, then we'll distribute the front here. So we've got 10x squared minus 4x all over x squared plus 1 squared. Y prime equals, now I'll go through and I'll distribute the negative, 5x squared plus 5 minus 10x squared plus 4x all over x squared plus 1 squared. And then one final thing is just to clean up the top in terms of combining like terms. So here we get negative 5x squared plus 4x plus 5 over x squared plus 1 squared. Now, we would look to make sure that we can't factor the numerator into something like this that would cancel out with the denominator, because that will happen on occasion. But I can just look and tell there's no way that we can factor that numerator so that it contains a factor of x squared plus 1 that would cancel out in the denominator. But do definitely look for that, and we will run into problems where that happens. Okay. Let's look at example 5. So the directions here are a little bit different. Instead of just saying find the derivative like we did in example 4, it's asking us to find the equation of the tangent line of the graph of this. Right, again, this is very obviously a quotient right here, which is good that we can recognize that easily. And again, to find the equation of a tangent line, we need to be given a point at which we are finding the equation of the tangent line. So here we've got the point negative 1, 1. If you remember from our conversation in class on Tuesday, we said that there are two forms of the equation that we could be talking about. The y minus y1 equals m times x minus x1. And the second is y equals mx plus b. Right? But it's very obvious that this is not the y-intercept right here, so we must be using this top one, not the second one. Right. The second thing we need to do is find the slope. So we know which equation we're going to use. We know what our point is. We need to find the slope at x equals negative 1. Again, remember, we hear slope and we associate that with the derivative. So we're going to take the derivative. Right. Now, before we do that, there are a couple different ways that we could go with this. It's very obviously a quotient. But the thing that is a little bit unfortunate here is that this thing in the numerator is not, it's not a nice polynomial like this one is. We could just go ahead and change this to a 3 minus x to the negative 1 and take the derivative like that. But there is an easier strategy to use in doing that, and that is to multiply top and bottom by x. Again, clear the fraction out of there. All right, so the first thing we're going to do is multiply top and bottom by x, right? And so when we do that, we end up with an equivalent fraction, f of x equals 3x minus 1 over x squared plus 5x. Again, it's just going to be much, much easier to take the derivative at that point. Okay, so then let's go ahead and do that. All right, so again, our first step was do a rewrite. And then next thing we're going to do is take the derivative. So let's use the quotient rule. So it says take the bottom, x squared plus 5x, times the derivative of the top, which is just 3, minus the top, 3x minus 1, times the derivative of the bottom. Hopefully you said that was 2x plus 5, all over the denominator squared. So we've got x squared plus 5x squared. All right, again, the calculus is over. Now we're just going to algebra. So here we've got 3x squared plus 15x minus, I'm going to leave this in parentheses first and distribute the negative later. So I've got 6x squared plus 15x minus 2x minus 5 all over x squared plus 5x squared. Sorry, I hope I'm not dropping out of the screen. All right. We could, at this point, keep simplifying, but I know that I want to find the slope at -1. So instead of going on and simplifying more, I'm not sure whether it would be better or worse if we were to do that. -1 is going to be pretty easy. Let's just go ahead and put our -1 in here. All right, so 3 times negative 1 squared gives us 3 minus 15 minus, I am actually going to change this to 13x. So minus 6 times negative 1 squared gives us 6. 13 times negative 1 is minus 13. And then minus 5 all over negative 1 squared is 1 minus 5 squared. Again, feel free to keep simplifying until you get to something smaller, but I'm just going to, for space sake, I'm just going to plunk that in. So we've got 3 minus 15 is negative 12, minus, and then 6 minus 13 gives us negative 7. Negative 7 minus 5 gives us another negative 12. And then we've got negative 4 squared, which is 16. Wow, that's nice. Negative 12 minus a negative 12, those cancel out, and we get 0 over 16, which is 0. All right, so again, we know we're using this form of the line. We know this is our point. Our other thing we had to do was find the slope when x equals negative 1, and we found that m equals 0 there. All right, so writing the equation of the line, then we're going to say y minus y1, which is 1, equals m, which is 0, times x minus x1, which is minus negative 1 or plus 1. This whole side just cancels out, so we end up with y minus 1 equals 0, or in other words, y equals 1, is the equation of the tangent line to the graph of this function right here. Okay? All right, next page. All right, using the constant multiple rule. So what they're trying to do here is point out to you that there are times when it looks like a quotient, but if we do a little bit of algebraic work, we might be able to end up rewriting this as not as a quotient, but instead as just a power rule. So in this case, we could rewrite this function. Instead of writing it as x squared plus 3x over 6, we could look at this 6 as a 1/6 or a scalar. And so the rewrite for this would be y equals 1/6 x squared plus 3x. Again, now that we have this scalar, we can just use the power rule that we did before. Right, so this would become y prime equals 1/6. Again, we leave the scalar alone, and then take the derivative of the inside, 2x plus 3. Right. At this point, the simplify part would probably be just put the 6 back in the denominator underneath where we had it, so 2x plus 3 over 6, or I wouldn't care if you distributed that and you got y prime equals 1/3 x plus 1/2. Either one is fine with me. Okay. Again, same thing here. We just also happen to have a coefficient up front instead of just a denominator like we did in the previous one. So our rewrite would be to acknowledge that this 5/8 is the scalar, and then we have x to the 4th. Okay, and then we take the derivative, so y prime equals, we're going to bring that 4 down to the front, so 4 times the 5/8 times x to the 3rd. We're going to cancel out right here, so we end up as our final answer, y prime equals 5/2 x to the 3rd, or 5x to the 3rd over 2, either one. Okay, this next one really looks like it is a quotient rule, but let me just point out that if we pull this 7 out with the 3 right here, so we rewrite this as y prime equals negative 3/7. Notice that each of these other two terms that are parenthetical up here have an x, just like this x in the denominator, and we can cancel out those 3 x's that are in common. What's left in the parentheses then ends up becoming 3 minus 2x. All right, so when we go to take the derivative, again, our scalar is going to stay negative 3/7. And then we take the derivative of what's inside here. That's just a negative 2. And our rewrite, or our simplify, is going to be y prime equals positive 6/7. That is, if you can pause first and just look for things like that, that is going to save you so much work. This is far easier than if we had used the quotient rule to do that. All right, and again, the last one right here doesn't necessarily look like it's not going to be a quotient rule. Again, we've got something in the denominator here, but we could rewrite this as y prime equals 9/5 times x to the negative second. Right, then we take the, I'm sorry, I don't know why I was writing those y primes here. They're not, that's not the derivative. This is just the rewrite. Sorry about that. This is the actual derivative in the next column. Right, again, this -2 comes down front, so then it's -2 times 9/5 times x to the negative 3. And then our simplify is -18/5 x to the negative 3. Probably the textbook is going to have it written as y prime equals -18 over 5x to the third. That's probably the preferable one. Okay, just a couple more things here and then we'll stop. In the earlier part of this video, I told you that we would end up finding out what the derivatives of the other trig functions are. And so it's telling us if we're going to take the derivative of tangent, we get secant squared. All right, we could work that out if we wanted to. We know that tangent is sine over cosine. And now that we know what the how to take the derivative of a quotient, we could do that. If you wanted to just do that as an exercise, you could do that and you would see that you end up getting secant squared. The derivative of secant of x is secant x tangent x. Again, secant is 1 over cosine x, so feel free to do a quotient rule for this, and you would end up getting secant x tangent x. This is a typo here. This should just say derivative of cotangent of x, not cotangent squared. Sorry about that. So if you would just scribble that out for me. The derivative of cotangent is negative cosecant squared. And then the derivative of cosecant is negative cosecant cotangent. I would just say, please commit those to memory. All right, there is no other way that I can think of other than deriving them each time by using, again, here you would do cosine over sine. Here you would do 1 over sine. You could get all of them, but it's just faster to memorize them, so please just memorize them. Okay, let's take the derivative of these two trig functions, and then we will stop for right now. Okay, so again, this is in the section on product rule, so we have to check to make sure that this is actually just a difference, that there's no product involved. All right, so again, that's just a plain old x, that's fine. This is just a plain old tangent, that's fine. Again, it's not just tangent times x, this is tangent of x. Tangent and a variable or a variable expression have to go together, so don't look at that and see a product. It would just be something out front that would be multiplying by it. So here we've just got two separate trig functions that are, or two separate pieces that are being subtracted. We just take the derivative by itself. All right, so the derivative of x is just 1 minus the derivative of tangent is secant squared, so this is going to be 1 minus secant squared x. You might be able to use trig identities to simplify some of these, and we will later on, but for right now I would say let's just leave it like that. All right, but part B says y equals x times secant x. Right, this is a product right here. Again, what's in front of the secant is not just a scalar. It's not an x minus secant, which would separate it into two different terms. This is an x times a secant, so this is the product rule. All right, so if you remember, the product rule says write down the first times the derivative of the second. The derivative of the second, the derivative of secant, is secant times tangent, plus the second times the derivative of the first. All right. So the only way I would clean this up, if I were to just do the most basic thing, this would be just x secant x tangent x minus secant of x. We wouldn't bother to write that one there. But the other thing you could do is you could notice that there is a secant x in both terms and factor that out. So this would be x times tangent of x minus 1. Sorry, I don't know why I switched that to minus 1. It should be plus 1. All right, so either of those would be fine. Okay, hope that was all right. Let me know if you have any questions, and hopefully I will see you on Tuesday. Bye.